Hey, how's it going, everybody? So, welcome back to episode 4, and we're going to talk about symmetry, Lie theory, and classical integrability. The theme here is that the solvability of a differential equation is determined by its symmetry. And we'll walk through these concepts step by step, but I just want to show you that there's kind of these algebraic miracles that make certain differential equations exactly solvable, and while others kind of descend into chaos, and it becomes really a matter of symmetry. So, typically, if you've heard this word thrown around a lot in physics, right? Symmetry, conservation laws. But really, when you think symmetry, you should think certain differential equations that possess certain symmetries are exactly solvable, and we can get the intuition behind the equations rigorously and mathematically to highlight how geometry essentially is ruled by algebra. And we can begin really in earlier episodes. We saw that specific tricks like Bernoulli substitutions or integrating factors for solving equations, right? And not Bernoulli, the Riccati equations specifically, they have kind of this geometric underpinning. But now we can discover that the geometry itself is governed by something we call algebra. And the fundamental question is why some equations are exactly solvable, right? And again, the answer to this is symmetry. When a differential equation emits a continuous group of transformations, and this is known as a Lie group, any group that is continuous, it maps solutions to solutions. So we can leverage that symmetry to reduce the equation's order and uncover conservation laws. And in exceptional cases, systems will possess infinite symmetry that leads to completely integrable systems. So nonlinear waves, called solitons, will behave like fundamental particles, and they can pass through each other without scattering and preserve their form and identity. Okay, so that's kind of what we'll discuss here and why symmetry permits such things to happen. Lie symmetries and prolongation. Okay, so Sophus Lie realized in 1880 that many integration techniques were manifestations of invariance under group actions. So, and we covered this really extensively in the initial conditions playlist, invariance in algebra. But if you consider a one-parameter group of transformations on the plane, mapping x and y to some tilde x and tilde y, so we're just transforming this, that depends on some parameter epsilon here, okay? This group is represented by something we call its infinitesimal generator, or its vector field generator. And this vector field, C of x comma y partial over partial x plus eta x comma y partial over partial y. This is the vector field generator, okay? And since the differential equations involve derivatives like, y prime and y double prime and so on, we must extend or essentially prolong the action, this action with this map to something we call a jet space, which includes coordinates for higher derivatives. And so essentially we're treating, or essentially a prolonged vector field, we'll denote as p to the n, p to the parentheses n, okay? This will be v, plus eta 1 partial over partial y prime plus eta 2 partial over partial y double prime and beyond. And so to prolong the action of the group, or a prolonged vector field onto this thing that we're defining as a jet space, really gives us, coefficients, eta k, that are computed actually recursively. And so, for example, if we have some eta of 1, right, we could take that, essentially we could compute that the coefficient would be d sub eta minus y prime d sub x c, where again this d sub x is the total derivative of that. Okay, it's the total derivative, or the Frechet derivative. Okay, and the symmetry condition and we discussed the Frechet derivative as well in the initial conditions. So there's a reason why I decided to make a playlist entirely called Initial Conditions before we talked about differential equations. Because you can't really meaningfully talk about these things and solving differential equations unless you have that kind of some kind of intuition for what's going on here. But what this allows us to do is have a symmetry. We can impose a symmetry condition onto this prolonged vector field, and again, this prolonged vector field applied to a differential equation f to be equal to 0 wherever f is 0. Okay, and so by doing this, the prolonged vector field or that jet space leads to a linear PDE that's called the determining equation, and which we will use this determining equation to find the symmetries V. And with these symmetries, we can introduce canonical coordinates to reduce the ODE, the ordinary differential equations, order by 1, and essentially divide this entire equation by a symmetry group. So we can show this. We can show the ODE directional field transformations, and what exactly this does in terms of computing the solutions. So a Lie group flow. We can define a Lie group flow on an ordinary differential equation vector field, and here we'll see the direction field for dy by dx or is equal to f of x and y, with some superimposed vector field v that's representing the symmetry. Okay, so let me just move this parameter epsilon. So again, this is the superimposed vector field, the original one, and then some symmetry that we are imposing. Okay, and this would essentially give us the plane as we vary the essentially the vector field v that represents the symmetry. We can vary the group parameter here epsilon, and what this allows us to do is the plane will flow along v. As you can see, it will flow along the symmetry v, right? And crucially, the integral curves of the ordinary differential equation are permuted, but they are intact. So the solutions map to solutions themselves. And so for a linear ODE, like y prime is equal to x or y minus x, right? This is a linear. This is the linear ODE. Y prime equals y minus x. Or we can look at a nonlinear one. All right, let's move the nonlinear one over here and vary the field. As you can see, here's a nonlinear one. And hopefully you can see why it's nonlinear, because there's a rotational component, right, where we have some y prime is equal to y squared minus x. We can observe how the direction of the field at transform coordinates moves with the grid, right? And the symmetry here is scaling x is equal to x partial x plus y partial y. So these points will scale again as e to the epsilon and y to the e to the epsilon. Okay, so they're scaling in such a way so that the original field, again, is shown in this. The original field here is shown, right? This is the original field that we're trying to model, and the symmetry vectors in the red and grid points mark the deformation that's happening as we perturb or as we vary the group parameter. But this can rigorously show how the symmetry preserves the solution structure as the transform field aligns with the ODE at new points. Okay? So next, this directly leads to the concept of Noether's theorem. Okay, and Noether's theorem says that for systems derived from a variational principle, symmetry yields conservation laws. So consider an action. We'll call this the integral of the Lagrangian, which is a function of the coordinates and the velocities, or the generalized velocities of those coordinates, plus time. And that action here is going to be minimized to give equations of motion. And Emmy Noether's theorem in 1918 states that if the action is invariant under a continuous symmetry generated by the original vector field that we are, or the original symmetry vector field that we are originally trying to construct its vector field generator, what that tells us is that there is a conserved quantity Q, constant in time, and the action is invariant under that continuous symmetry generated by it. So this bridges algebra to physics, because time translation symmetry implies conservation of energy. Spatial transformation, or spatial translation, conserves momentum, and rotation conserves angular momentum, and gauge invariance conserves charge. Okay, and hence that's why Q dq by dt is equal to 0, because that's charge. Okay, and so choosing particular gauge symmetries, or choosing particular rotational invariants or rotational symmetries, or spatial translation symmetries, or time translation symmetries allows us to then invoke the method of prolongation to describe canonical coordinates for solutions to differential equations within the jet space. Okay, so we can test this numerically here. This is I'm calling it Noether's machine, but really I'm going to show you the time symmetry and energy conservation, or just conservation laws in general. But really for let's just say if we, for Noether's machine, if we apply this to a pendulum system, okay, so this is a pendulum system, roughly, okay, small angle approximation, with a Lagrangian, 1/2 ml theta dot squared minus mg, what, I don't remember, I think it's like 1 minus cosine or something, so double angle, whatever, right, identity. But this leads to theta double dot plus some sine theta term, right, equals 0. And so if you plot the angle sine theta here, that's essentially what's happening. Okay, so that's where you're getting this from. And for a time symmetry, we can see the energy is equal to 1/2 L squared omega squared, whatever the energy quantity is. All right, and that should be conserved. So here, this shows the plot. This shows a quantity. Here the quantity is kind of this flat line with a little bit of noise, as you can see, but look how minuscule the noise is. It's extremely, I mean, it's like floating point integer kind of precision happening here, maybe with a little bit of the small angle approximation, assumption. But at the end of the day, the plot shows the quantity as a flat line, and this dashed mean value here that we're showing here is the shaded kind of sigma region representing how constant it is. So variation is really really small. So it confirms this mathematical invariance, right? And this demonstrates how symmetry enforces these integrals of motion very rigorously. And we can also look at other, we can change the initial angle that we use here. So if we use a bigger angle here, we can have this. As you can see, the energy becomes a little bit less conserved over time, but still it's relatively small. And also we can look at angular momentum conservation to be pretty exact. Okay, so yeah. Well, so all right. what we can do here is completely the integrable systems. Completely integrable systems are basically showing that some nonlinear PDE or partial differential equations have not just finite but infinite conservation laws. Okay, so the archetype is called the Korteweg-de Vries equation, and there's some really cool. This is a really I would recommend. I should have put a picture of this, but this models shallow water waves. And it supports the idea of a soliton, or a localized wave that propagates without changing shape. And you can see like these waves of, like, if you've ever seen those square waves or whatever, they're usually trying to solve, or they're usually representing some Korteweg-de Vries phenomena, which is really cool. This is a really fun equation to use. But when the solitons, essentially the solitons of the wave, kind of, by the way, solitons are localized waves, again, that propagate without changing any shape. And when they collide, they interact non-linearly, but they emerge unchanged. And so aside from this, like, kind of, they shift phase a little bit, but the generic nonlinear waves might disperse or merge, okay? So, generic nonlinear waves might disperse or merge, like we saw in the caustics, but with the KdV waves, they have this special property of this exactly. So in the KdV soliton collider, if we watch two solitons with amplitude A1 and A2, okay, they have two different amplitudes. And of course, speed is going to be proportional to the amplitude. So say like C is equal to 4A or something. The wave here, we're plotting the wave itself, and we can show the solitons kind of approaching each other, right? Let's see this. You can see the solitons will approach each other, and the speed of the waves again depends on their amplitudes. But you get a boosted overlapping, right, with kind of a boosted peak during this collision due to the nonlinearity of them, but they separate cleanly from each other, and an individual kind of soliton profile, and these markers here are for the centers of those solitons. I didn't render the other one. Let's decrease the amplitude of this one. Maybe, can we see it? Yeah, I messed it up. But okay, let's assume they're the same. So they would technically, if they're the same amplitude, they would technically go the same speed, right? As you can see that. But if we change the amplitude of this first one to be much larger than the other one, we can see kind of how it just kind of traces over it, right? And so as time advances, the faster, this taller soliton is faster. It's going to overtake that slow one, but post-collision, both will retain their original forms and speeds and illustrate, that kind of particle-like behavior by the infinite symmetries. And so let's find one where the speed's pretty obvious. And so again, they have their original speeds here, they collide, and they have the same exact speeds again. Right? So the Lax pair and inverse scattering. We're going to take the Lax, or Peter Lax in 1968. This is actually past what we did previously, but he was messing around with inverse scattering problems. So nonlinear solvability arises because these equations are really are really linear in disguise in higher dimensions. So Peter Lax, again, in 1968, showed that the KdV equates to the compatibility of linear operators L and M, which give us basically the commutation of these linear operators that describe these solutions, or the solitons. And so choosing L of T, we can basically define the Schrodinger operator with potential U, and this commutator will reproduce the KdV solitons. So the eigenvalues lambda sub k of L are time independent, and d lambda sub k, or the rate of change of the eigenvalues, is 0. So that means that the nonlinear evolution is something we would call an isospectral flow. And an isospectral flow just means that the observables, or the eigenvalues, aren't changing. And so they're time independent. And that means that it's a unitary rotation, or the operator is encoded, or the space of the operator has a unitary rotation. Again, the space of the operator itself it obeys a unitary rotation symmetry. So that means that this enables the inverse scattering transform. So if we have a nonlinear Fourier transform, I'm not going to go really deep into the mathematics, but first, you can scatter some initial data and spectral data with eigenvalues and reflection coefficients, and then we can evolve this data linearly with trivial phases, and then we can invert this via the Gelfand, Levitin, Marchenko equations. I'm sorry. GLM equation, right? To recover the initial, or to recover the actual solution from just the initial data, okay? And through that inversion, that allows us to officially solve it. So we can look at the KdV isospectral evolution as well, just to kind of show this. But this top plot again is the evolving wave here, and I can just show you how, it's a moving KdV wave. It's a moving soliton. All right, that's all it is. All right, and but what's happening here is that and again, this wave here is starting as like some. Let's say the wave here starts as some like secant squared kind of potential, right? An evolving wave. It starts as like a 2 secant squared x, and it's shifting rightward. And let's say this is the initial reference of the lambda. Well, what we can do is, and again, the bottom part is the discrete eigenvalues computed with finite differences. These will mostly remain frozen, plotted, and we're going to plot these we're going to have markers that connect the lines with t is equal to 0 for references, whatever. And the max drift is going to be negligible. So we can look again at how we can evolve this wave, and look at how it did change a little bit, right, from negative 395 to like negative 398, right? We can really see this principle. We can really see the propagation of these this KdV isospectral evolution happening in principle, and this is kind of a numerical artifact that's happening from the grid mesh. But again, as the wave moves violently, the spectrum its constancy, it gives us this linearity. So even though we have, again, this is a nonlinear wave. It's a very nonlinear wave. Look at how it's like, essentially this wave here, it starts with the value of 2, this original solution, but then it starts to get really, really, it's a soliton, right? And it's an inverse scattering problem that we're using. So finally, what this allows us to do is then show that symmetry itself, again, represents the solvability of or linearity of an ODE, so of a PDE. So again, right, PDEs, if they're solvable, usually linearize them in some way, right, in terms of ODEs or in terms of whatever, right? We find some way to compute it, and the symmetry only kind of reinforces that, because in supersymmetric quantum mechanics, or SUSY QM, we can factorize the Schrodinger equation algebraically, and this is actually really important for quantum computing as well. But if we have some H minus, right, or we can have a Hamiltonian to be H minus, and we can also say that there exists a partner Hamiltonian, that shares the exact same energy spectrum, except possibly the ground state. This will then create a hierarchy of solvable potentials, or shape invariants. All right. And so how you can think about this is, we have A dagger A and then another A dagger A sharing the spectra. And this will generate a hierarchy of solvable shape invariant potentials. So, and of course, they will be linked by something called superpotentials. And this also has connections to integrability, because it's something called Backlund transformation. So we can tie, quantum mechanics and solitons and groups together. Also, in the next episode, we will talk about stochastics and rough pad theory, but also stochastic quantization also allows us to recover supersymmetric quantum mechanics as well. But okay, so that was kind of a rant. But we can tie really quantum mechanics, solitons, and group symmetries together. So in this visualization here, I just kind of want to basically show you how this works, which is that in supersymmetric partnering, we can select a potential like a harmonic oscillator. Just it's related to x squared, right? With w is equal to x over square root 2 or something. And the superpotential would be x over square root 2. But if we chose a superpotential of like in hyperbolic tangent, we can also get a solvable, nice shape invariant potential as well, which is secant squared. Okay, and both of these are essentially ways that we can show the energy levels as well, which are these horizontal dots right here, and with energy levels like k plus 1/2, right, or in or minus in one. Sorry, minus n minus k squared, right, for these like v minus potential here, and then so that would be the energy level that exists there for that ground state. But also we can, for v plus, if we shift it by 1, it'll align exactly with differences, and we can connect these lines again between the isospectrality of them here. And let's see, let's move it down. I kind of constructed, you can't really see it really well, but again, we're getting the energy levels that are associated with that, with these partner potentials, and they give us, essentially, they allow us to shift the energy levels by 1, and it'll align exactly with these, lines that highlight the isospectrality. But there is a missing ground state again in V+. And so this will show us how the factorization yields exact solvability. So again, just so that you can see this. This is the utility. So again, supersymmetric quantum mechanics is just another way to solve differential equations, except the operator space itself has a U1 symmetry. And so there you go. The Hamiltonian, obeys the it's kind of like a meta kind of symmetry. So supersymmetric really should just be called meta-symmetric, but it's okay. Or operator symmetric or whatever, I don't know. But anyway, so in summary, Lie theories, right, or Lie symmetries reduce orders to Noether conserving quantities, and then infinite symmetries enable solitons. Isospectral flows, solvability emerges as mere algebraic symmetry. Okay, so references again include works by Blumen and Cole on similarity methods, Korteweg, De Vries on the equation, Lax on integrals, Lie, Sophus Lie on groups, Noether on invariants, Oliver on applications. If you're interested, this really goes into depth on the methods of prolongation and jet spaces, and even touches on jet bundles. Noether on invariants, Oliver on applications again, Witten on supersymmetry, and Zakharov and Shabbat on exact theories. Okay, thank you for joining me on this mathematical kind of journey, and I will see you in the next episode. Thank you.